data validation with predictive analytics. I would like to invite everyone to please type in any questions or comments you may have at any time using the Q&A tab at the top of your screen. I do not mind being interrupted, and if I say something that's confusing to you, it's likely confusing to everyone else. All right, we hope you enjoy the web seminar and find it a useful use of your time. Now, my name is Bill Goebel. I will be doing your web seminar today. I have a lot of experience in industrial automation, and a lot of the time I've spent, especially in the last 30 years, has been studying field failure data, which is what we are going to be talking about today. I work for FMEDA. FMEDA is a global corporation with worldwide locations. FMEDA does a lot of different activities, including systems level consulting, training, tools, and we have reference materials where we publish a significant portion of our failure data research, and we have a strong product and professional certification group who has now performed most of the certifications in the process industries. In terms of our engineering tools, we have a suite of tools that cover the entire safety life cycle and related activities, including alarm management, process hazards analysis, SIL selection, SIL verification, and if you look at the very bottom, the SILstat data collection tool. SILstat has been serving us very nicely with data coming in from end user applications with their permission from around the world. Many customers are using our data analysis services, which we will describe to a certain extent today. We'll be talking about the predictive analytics technique. FMEDA has published most industry references on automation and safety. I'm quite proud to be part of a group where we don't hide our results and our research. We publish them so everyone, and of course we charge for it, so everyone can use it and we can make enough money to pay for more research. All right, let's talk about field failure data validation. Who cares about field failure data? And why are we even here? Well, certainly one of the most, the fundamental concepts from our functional safety standards is the probabilistic performance-based design. And many of you know that it was terribly controversial when it was first proposed, and even to this day, there are many people who prefer a very prescriptive canned design type approach rather than allowing engineers to create new and innovative designs. The advantage of this is that not only can engineers actually do engineering, but we are allowed to optimize our designs to match the risk and to match the variables of our plant. In the roughly 15 years since these standards have been released, many people have taken full advantage of these attributes, and the whole probabilistic performance-based system design approach is becoming rather commonplace. Part of that, of course, the other fundamental concept is the use of the safety life cycle, a detailed engineering process intended to reduce design mistakes. As part of the detailed safety life cycle, there is a section, a series of steps, a section of the life cycle, and a series of steps where we perform the probabilistic performance analysis. Now, many of you know how to do that, and FMEDA has an entire web seminar on the 3 barriers to SIL verification, It is recorded and available on the Exida website as well as YouTube. And so if you want to see the details of how to perform this step number 11 on this drawing, please feel free to look at the web seminar. The key point for now is very simple. In order to verify a design in terms of its failure probability, we must have realistic failure data. This, of course, was the key point of debate when this whole concept was being proposed, because there were many who simply said there is no such thing as realistic failure rate data. We don't have the information we need to implement this standard. One Sunday morning when I was looking at the paper, I've gained some insight from cartoonist Scott Adams. People have kind of a bad attitude toward failure data, and I have to admit, when I've studied some of this failure data, I began thinking the same way. According to Scott Adams, the way to create a set of failure data is start by typing random numbers into a spreadsheet. And then you're done. I know some data seems that way, but it isn't if you start digging in and studying. There are many sources of failure rate data. Industry databases are an excellent source and a valuable way to get data. Manufacturers' field return data studies have some value, although we have to be extremely careful about the assumptions used. It's most valuable, in my opinion, for gathering up root cause failure analysis reports, which manufacturers typically do. There is the B10 approach used in mechanical and electromechanical products, primarily out of the machine safety arena. But you've got to remember, machines typically move fast, and the primary failure mechanism is wear out. And so we've concluded, of course, that you have to be very careful about manufacturers' field return studies, and B10 cycle testing has no place in the process industries and is extremely dangerous. And user field failure data studies are probably the most excellent source for potential data as we move forward. But unfortunately, many of their systems are quite weak, which we will talk about in great detail. And of course, the FMEDA technique developed by Exida is a predictive failure rate approach, which can produce very good results if it's properly calibrated. I'm a fan of ORITA. ORITA is a consortium of offshore companies in the North Sea. It's operated by DNV out of Norway, and data analysis is done by Syntef. And it provides very useful data on process equipment in very generic categories like final element assembly. It's updated every few years, and I keep up to date on it. I study it. A group from Exida even went to Norway and reviewed the data collection and analysis techniques with some engineers from Syntef. The problem is it's a bit hard to use in safety instrumented function design, as the data is significantly aggregated. That sounds like a mighty fancy word, but what it means is you can't get the detailed failure data for a particular type of solenoid valve, a quick exhaust valve, a rack and pinion actuator, a piston actuator, a butterfly valve, or a ball valve. You can't get specific data for a particular brand of PLC. You get very generic categories. And how do you know if your design matches the category? Well, you just got to do your best. And, of course, data is not available for many years after a new product is designed. And you'd be quite shocked how often that happens, even when you don't think it does. Manufacturers are redesigning all the time, sometimes because they must. Parts go obsolete. End-user field failure data studies, on the other hand, I've said represent the highest potential for good field failure rate data, but we must overcome a number of problems that we have found to be quite chronic, including insufficient information in the failure reports, different definitions of what is a failure, and different data analysis methods. But these problems can be solved, as I will talk about some more. Don't forget, questions or comments, please ask. Why are there all these problems? Aren't there field failure data collection standards? Well, yes. IEC 61508 refers to this ISO 14224 and IEC 60300-3-2. And there is also the NEMOR NE93, and they all do set up a framework for data collection. But what we've discovered is that there's not nearly enough detail in there to do a proper job. And perhaps most importantly, many people aren't even following those standards. But it's okay. We can solve the problem. We must be very careful of the input data we have from a set of field failure. I once talked to an engineer who was quite proud of their data analysis. And he basically said, I could hire a statistics expert to completely analyze this data. And he did, and they had a lot of very interesting numbers. And I said, how do you know your numbers are right? All the statistical expertise in the world cannot identify bad data or, perhaps more commonly, inconsistently classified data. So if we want to set up a good field failure data collection system, how do we do it? What kind of a system should we have? A group of us at Exeter have collected over 150 billion unit operating hours of process equipment field failure data from over 100 locations, some of it from direct end users, some of it from manufacturers, which we use to identify failure modes and root cause, and some of it from our SILSTAT users who have elected to allow the data to be sent to us. We've learned many different systems. We've discovered many different types of data collection, and we've discovered a number of different lessons. We've taken all this information and integrated it into a set of techniques which we call predictive analytics. Now, what is predictive analytics? We're looking for a way of validating a failure rate number, at least checking it for reasonableness. So we start with our knowledge of design strength from actual products. Everyone knows that failure rate is a function of stress versus strength. I've always been a big believer in that kind of a general philosophy. I learned it at the Eindhoven University of Technology from Dr. Brombecker, and it just made sense from the day I learned it. We can evaluate the design strength of a range of different products. And at Exeter, we do that through our FMEDA technique. It is an analysis of design strength. And by looking at a large collection of products, we can tell how the design strength varies from product to product. So the concept is, given a consistent environmental stress operating profile, it's called, we can predict how the failure rate will vary as a function of the variations in design strength of the products. We're very lucky to be able to have this extent of data to be able to analyze. And what we do, for example, here's a slide showing a study of the design strength of 35 different pressure transmitter designs, combined with field failure data from ARITA and from Dow. and we show outlier limits and expected range. And we can tell by looking at this chart, we can establish a set of numbers for a pressure transmitter. And based on the analysis of this set of data, we can predict how well a set of field failure data, or we can predict how well a data collection process for field failure data is working, and whether they are collecting information properly or whether they have some serious problems in their data collection process. Here's what we do. We take a set of field failure data that we get from the field. We perform statistical analysis on it using one of several different techniques to produce an estimated failure rate. We take the predictive analytic model for each device type, including the upper bounds and lower bounds and statistical averages and deviations, and we compare the actual estimated lambda with the predicted lambda range and ask a number of simple questions. Are we out of range? How far are we out of range? And what is the probability that the data collection process is inconsistent with norm? We study the data collection process, and the failure categories and issues can be resolved for the purposes of creating consistent and realistic failure rate estimates. Not a bad approach. When all that is done, we often find problems in data collection. We fix them, and customers get much more useful and relevant and realistic failure rate data. It's been quite an interesting experience. An extensive set of test results from a test shop indicated that a manufacturer had an exceptionally low failure rate when compared to our predictive analytic bounds. All right, out of range, not credible. So we took a visit to the test shop to learn exactly how the instruments were evaluated and classified as a failure or not. Look at this. What we discovered was that before each instrument was tested to see if it failed or not, it was cleaned up. Cleaning included, you won't believe this, disassembly and replacement of seals and O-rings. And I was thinking to myself, I'm shocked that any units failed after that refurbishment activity. The key lesson learned is the test and repair and data collection process must be understood to correctly analyze field data, and the predictive analytic bounds flag the need for an extensive data collection process review. Key point, as found conditions must be recorded. And although I have to say I'm a little surprised how often that does not happen, but it is an essential component of any good field data collection system. In another incident, we discovered that data from an on-site repair shop in an end-user facility is entered into a maintenance management system where equipment failure rates are automatically analyzed. The MMS report showed the failure rates of some instruments being used in a safety function were much lower than those used for SIL verification in the Excellentia tool. Therefore, they concluded they could extend proof test intervals without sacrificing their necessary risk reduction. However, before proceeding, a wise instrument engineer visited the test shop, and he discovered that failure reports were entered into the MMS only when a device was sent out for repair. In other words, the only units that were considered failures were those that had to be sent out, because that's how a repair order was generated. All units internally repaired were not recorded as a failure because they didn't need a purchase order. Oh my goodness, it's no wonder the data was extremely low. The proof test interval was not extended. The test, repair, and data collection process must be understood, and as found conditions must be recorded. I have a whole lot of stories, and you don't want to hear them all, but I've got one more. A field failure study of a valve showed a very low failure rate when compared to the Exida PA benchmark. The conclusion was this valve would be excellent for safety applications. And we discovered that the valve was designed and manufactured for control applications. And in the analysis of field failures, nobody ever recorded whether the device was being used in a control application or in a safety application. And many of you know and understand that any mechanical component used in an application where it's frequently moving has very different failure rates and failure modes than a valve used in an application where it's typically not moving. Binding, stiction, cold welding, all potentially dangerous failure modes. It's no wonder this low failure rate was outside the reasonability limits of the PA benchmark. Lesson learned, application conditions must be recorded and listed in the analysis report. I see a question. It seems you place more faith on predicted lambdas using FMEDAs than field data. And certainly you pointed out some good examples of this. Yes and no. What you need to know is the information in a previous web seminar where we explained how it's important that any predicted lambda be based on field failure data that's already been validated. So you might think of this whole process as a closed loop feedback mechanism. Validated field failure data must be used in an FMEDA to get realistic results. Exida definitely has a very detailed paper talking about how we constantly compare FMEDA results, predictive lambdas, to the validated field failure data that comes from the field. You kind of saw that on the slide, but different emphasis. Let me go on. However, the predicted lambdas with FMEDAs also come from manufacturers' data. Absolutely not. Nothing done by Exida is based on manufacturers' data. I will readily admit that other certification bodies and other people doing FMEDAs do use manufacturer's warranty data, which, as I said, is typically quite optimistic. So don't think about FMEDAs as being the same from one group to the other. The database must be field calibrated. We have a whole web seminar on that, and we've done it before. You can see the recording, or it's coming up again in a few more weeks. Another question, thanks. Did this example use the control valve in an SIS application with a separate solenoid? Actually, yes. Actually, we don't know because application conditions were not recorded in the failure reports. So we had insufficient information, but someone used that information to calculate a failure rate without even knowing the application. So we're looking for reasons why the failure rate might be so low. It's way outside, it's way below reasonable limits. And one potential explanation might have been that all these valves were being used in control applications where they were moving. And that is very different than applications where the valve is static. Now you might be asking, whoa, what about when I use a solenoid valve with a control valve? Well, if the control valve is moving and it is being used in a dynamic application, then a dynamic FMEDA would indeed generate a lower failure rate. And Exeter has recently finished our complete characterization of mechanical components to include both static and dynamic operating conditions. Although that was a lot of research and it's just finished last year. So you'll see some of those data points coming from us. Thanks for the questions. Please keep asking. I'm happy to answer any set you want. Okay, field failure studies. We see that they exist, they can be valuable, but the outputs have to be checked for reasonability. The data collection process must be checked, and when that is done, then that data is what I call validated field failure data, and we use it to calibrate the FMEDA results in a nice closed-loop system. We also use predictive analytics to identify product-specific failures versus site-specific failures. And what I mean by that is, I find it a fascinating subject. Several data sets, once the data collection process was validated, have indicated a 2x difference in the failure rate from site to site for the same product model number. Did you hear me? Okay, let's say I've got this brand XYZ pressure transmitter, and it has a failure rate of 3 times 10 to the minus 7 at one site, and it has a failure rate of 6 times 10 to the minus 7 at another site. Is that because they're collecting the data differently at these two sites? Well, perhaps, but once it was determined that was not the case, then we went into root cause analysis and determined a difference between product-specific failures. Was it an internal failure, or was it caused by a weakness in the product selection process? They were picking equipment with bad materials, they were maintaining them wrong, they were testing them wrong, or they were repairing them wrong. And this is really a benefit of data collection, because you can actually identify site-specific causes and fix them. So what am I saying? You can actually reduce the failure rate by doing root cause analysis, and that's especially valuable once you have a validated data collection process. I'm absolutely sure that a good data collection system can be implemented without major expense. It has been done at many sites, and we have quite a few of those now that are feeding back high quality data with a validated data collection system. We use the predictive analytic statistics as a benchmark to tell us how deep to dig and how good a data collection process might be. Anytime there's a discrepancy, you must explain why, and the more you explain, the more benefit you get from the data collection. Anybody else have any more questions? I know I'm moving pretty fast today, but we like to keep these things way under schedule. I would like you to know that a very detailed paper on the predictive analytics process is being presented, I said next week, I mean 2 weeks, at the Texas A&M 70th Annual Symposium in College Station, Texas. And the paper will be available on the www.exeter.com website under the Resource White Paper section. Of course, the paper is written and it will be posted shortly. Any other questions on data collection and analysis? I see another one coming in. Okay, let me just check here. It says, how much data was used to validate the FMEDA component database? At this point, Exeter has collected 150 billion hours of total unit operating data from both manufacturers and end users. I would say a majority of it is from the manufacturers, but some of the best data is actually from end users. Probably the first one that pops into my mind is a power generation site where they seem to collect very good data. So the answer is 150 billion unit operating hours of all different types of instruments. We will not do a predictive analytics analysis on a product type until we have at least 100 million unit operating hours on each product type. That has taken us over a decade to compile, but now that we have all this data, we're going to use it to better improve data collection, so we better improve the predictions. And it works in a nice positive spiral feedback mechanism. Any other questions? Anyone who wants to see a recording of this or to get a copy of the paper written on this subject, look on the exeter.com website. Okay, there's another one. Thank you. A quick question about the generic SIL3 certified logic solver data in SERH. Is this, good question, is this a worst case in class? The answer, yes. I could mark it on a slide, but I did not. But we use the Predictive Analytics statistical results to also establish the Exeter generic failure rate data. The concept is, if you ask for a generic set of failure rate data, we have to assume it's one of the worst designs of the entire class. The worst design. We have to assume that. This is safety. So we will look at the predictive analytics statistics, and we will pick a value very close to the outlier result which you saw on a previous slide. I'll show it to you real quick. Remember this slide? The Exeter generic failure rate data for a pressure transmitter will be roughly right here on the outlier limit, because we have to account for the worst possible design, the weakest design, the one that will give you the highest failure rate, because you might be using that one. Make sense? Hope so. Sometimes perhaps we might be too conservative, but I think it's good. How to find or validate failure data from valves that are not SIL certified. Exeter does a lot of FMEDAs for valve manufacturers. That is a method of predicting a failure rate. As you can see that, in fact, you can probably see right on this slide, most of the FMEDA results are down here in the expected range, and they compare very nicely with actual field failure data from both ORITA and from Dow. However, some of the designs that are actually in the market are not so good. They're weak, and they have failure rates that are higher. The bottom line is, you either must have your own field failure data, or you must have a credible FMEDA. Now, I know products that Exeter certifies, and we've done probably 95% plus of all the valves in the market. Let me just think if I can think of any other good solution for you. If you are very confident that a valve has a design that's very similar to and has the same strength as another valve that is SIL certified, you might consider estimating your own failure rates by looking at the numbers of similar designs. I have done that as a technique, but of course then, since you're never sure, you would want to use a safety factor. I usually use at least a 2x safety factor when I do that kind of a thing. So, how do you find or validate failure data for valves that are not SIL certified? Well, even valves that are SIL certified. You take a look at other numbers and compare. You can do your own data comparison, and you can see all the FMEDA certificates on the FMEDA website in our Safety Equipment Reliability Database. And you can see the failure rate numbers on the FMEDA certificates, and you can come up with a number of your own. We are creating an application which will allow people to use our predictive analytics results to check and validate, at least check for reasonableness, any failure rate data of any product, including valves that are certified or not. Hope that helps a little bit. In other words, find information, write it down, and compare. Of course, you might go to that vendor and say, hey, you need to get your valve certified. Of course, that kind of a thing's okay with me. All right, I thank you all very much. Any other questions? Please do not hesitate to send an email. Oh, another one came in. Thank you so much. If failure rates from the component database that FMEDA uses in their FMEDAs are validated with field data, why do we want operators to collect failure data? That's a good question. And I'll finish. I would believe that properly collected field data is stronger than generic failure data. I would believe that properly collected field data will give you a failure rate lower than generic failure data, at least the generic failure data from FMEDA. So, however, I'm not familiar with FMEDA component databases, so I cannot really comment. Okay, let me deal with your first question. If failure rates from the component database that FMEDA uses in the FMEDAs are validated with field data, why do we want operators to collect failure data? And the key answer is let me call up that slide. The key answer is right here. If you collect data, you will be able to identify and sort the difference between product-specific failures and site-specific failures. What I'm saying is, if you have a good data collection process that has been validated and reasonable, and yet you still find a failure rate that's higher than it should be, you have a problem that you can fix. And we've found many examples like this. And when those people identify those problems, they reduce the failure rates of their equipment. What kind of problems? Well, it might be in the product selection process. Perhaps you're picking products that aren't suitable for the stress conditions of your application. Perhaps there are problems in your maintenance procedures. Oh, I have many stories, but boy, I won't give you names, of course, to protect the guilty, but I've heard of many products that were damaged during proof testing and many products that were actually damaged due to incorrect repair procedures. Your data will help you find these problems if they exist at your site. And if they don't exist at your site, it will confirm that you have a good safety culture, a good maintenance capability. FMEDAs are a good way to get started, but FMEDAs, to be very clear with you, only give you the failure rate for product-specific failures. Thanks for that question. Very insightful. Appreciate it very much. All right, just want to say if you have any other questions, please don't hesitate to send an email. I can answer it asynchronously. I'll type my email address for anybody that doesn't have it handy. Oh, I appreciate comments at any time. You can send me an email and I'll answer it asynchronously. I just can't promise to answer it very quickly because sometimes I get quite a backlog. I thank you all very much for your attention. If you want to see, you will be sent a set of data, or a set of these slides, and you will be sent a link to the recording if you want to go back and look at something else again. Thanks very much for your time and attention, and stay tuned for the Wednesday web seminars from Exeter. Goodbye.